Our goal in this series of lectures is to derive something called the binomial theorem. The binomial theorem is really almost more of a formula that lets us expand binomials, something like x plus 1 to the 100th power, for example. It lets us expand that out really, really efficiently. As a matter of fact, you could even do it by hand for relatively large exponents without too terribly much trouble. So the process for doing that starts with this thing here. It's called Pascal's formula, right? It goes back to the famous mathematician Blaise Pascal. And it's got combinations in it, so you can kind of see how it fits into what we've been talking about in the rest of this chapter. But beyond that, I mean, just looking at it, it's hard to really kind of see what it's saying. Now, there actually is a really cool underlying pattern to this. And before we jump in and start trying to show that this really is true, I think it's a good idea to stop and take a look at some specific numbers and see if we can kind of figure out what that pattern is. So what I've done here is first I put the formula, Pascal's formula, back up there at the top so we have it to reference. And then what I did is I filled in this little grid here. The n values are the numbers here in the rows, and the r values are the numbers here in the column. So what I've done is in every one of these cells, I have put C of n comma r. Right? For example, if I just kind of pick one here, if we look at this one is C4 comma 2, right? Because row 4, column 2. And you're welcome to get your calculator out, double check, make sure you convince yourself that really is what these numbers are. Okay, so now let's take a look here at the formula, right? And see what the formula has to say. So if I, as a matter of fact, let's stick with that one. If I pick this one here, right? What this is saying is if that's this value on the right, then the formula is saying if we go up a row, right, and would be the row before row n plus 1. If we go up a row, look at the number in the same column and the previous column. All right, so that's going to be this value and this value. And if we add them together, yeah, look at that. We get the value below it. All right, so let's try with another one. Right, if I look at this value here, right, and I do the same thing, right, if this is m plus 1, then I'm going to look at n, that's the previous row, same column, previous column. So I go same column, previous column, and yeah, look at that, 4 plus 1, sure enough, equals 5. Right, so this arrangement here, right, the way I've got this laid out in this triangular shape, it has a name. It's also attributed to Pascal. It's called Pascal's triangle. Right, and the way you'll see this, it's often written out in more of an isosceles triangle kind of shape. Right, you'll see it starts off 1 and 1, 1. Then there are a couple of other patterns. Before I start filling this in, there are a couple of other patterns I want you to see. Notice how this side of the triangle is always 1. Right, and that makes sense. This column is always C of n comma 0. And if you put that into the formula, right, you'll see what do you get here? You get n factorial over 0 factorial times n minus 0 factorial. And yeah, 0 factorial is 1. N minus 0 is n, so these cancel, and yeah, all you're left with is 1. So good, that is what we expect, right? And then if you look at the other side of the triangle, going down this way, you'll see that one is also always 1. And again, right, that is what you should expect. Notice how this is row 1, column 1, row 2, column 2, C of r comma r, or n comma n, whichever one you want to put in there. This is also always equal to 1. So I know as I'm writing it out in this slightly different shape that the outer edges of this triangle are always going to be 1. So when I go down to row 3 here, it's going to have a 1 and a 1, and this number in the middle, 1 plus 1 is 2. Right, then for the next row, I'm going to continue the ones. 1 plus 2 is 3. 2 plus 1 is 3. And you can keep going with this. 3 plus 1 is 4. 3 plus 3 is 6. 3 plus 1 is 4. And then we've got 1. You notice if you compare this to my triangle down here, yeah, I'm getting the same ones, right? I'm just kind of tilting the triangle over a little bit. And this, if you see this in textbooks, the upper version is usually how you'll see it written. It was more convenient to do it down here in this table format because you could really see what the rows and the columns were in a way that's a little harder in that particular shape. Okay, one more thing I do want to point out before we move on and actually start thinking about how we can show that this is true. Notice what's going on in the next row in, right? Starting here, 1, 2, 3, 4, 5. And we get the same thing going on here. 1, 2, 3, 4, 5. And again, you see that here and here. I want you to kind of put that in the back of your mind, right? Because when we start actually getting into that binomial theorem, recognizing that that's what that first inner column is doing is going to be a little helpful to make sure you're using the right row for whatever binomial it is you're trying to multiply out. Okay, so now that you kind of have an idea of what that formula is trying to say, right? Let's see if we can prove that it's true. And there's two different approaches that we can use to do this. One of them is just a purely algebraic method. We have a formula for these combinations, right? So I'm going to use that formula here, right? And I'm going to say like the left-hand side, if I put n plus 1 and r into my combination formula, this is n plus 1 factorial over r factorial times n plus 1 minus r factorial. Okay, so hold on to that. Now I'm going to go over to the right side. I'm going to start doing stuff over there on the right, and I'm just going to do some algebra manipulations and show that the right side is equal to this formula that I got here from the left side. Okay, so I'm going to use the formula again. This is n factorial over r minus 1 factorial times n minus r minus 1 factorial and plus n factorial over r factorial times n minus r factorial. Okay, I got two fractions on the right and I only have one fraction on the left. So the first thing that kind of comes into my head is, can I add those two fractions together? And yeah, I can do that. I'm just going to have to come up with a common denominator first. So what I'm going to do is I'm going to start by multiplying the top and bottom of this fraction by r. Okay, so that makes the numerator r times n factorial. Look what happens down here on the bottom. R times r minus 1 factorial is r factorial. And I'm going to clean up the parentheses here. This is n minus r plus 1 factorial. Okay, so what do I have to do over here with the other fraction? Well, I've already got the r factorials. That part's good. Over here I've got n minus r, and I need it to be n minus r plus 1. So I'm going to do the same thing that I did with that left-hand fraction. I'm going to multiply the top and bottom by n, whoops, not r, by n minus r plus 1. I'll do that here on the bottom. That makes the numerator n factorial n minus r plus 1 over r factorial times n minus r plus 1 factorial. Excellent. Now my denominators are the same. Now I can add the fractions together. So the numerator is r times n factorial plus n factorial times n minus r plus 1 all over this common denominator, r factorial n minus r plus 1 factorial. Excellent. Now, if you look at those two terms in the numerator, notice they both have an n factorial. Okay, well, let's pull that out. This becomes n factorial times r plus n minus r plus 1 all over that common denominator. R factorial n minus r plus 1 factorial. Now, good. Look at what happens in those parentheses. R minus r, that's 0. All that's left in there is n plus 1. Well, n factorial times n plus 1 is n plus 1 factorial over r factorial n minus r plus 1 factorial. Excellent. What I have here, the right-hand side equals this, and the left-hand side equals this. The two of them are, in fact, equal to each other. That's exactly what I wanted to prove here. So, that was a perfectly good proof, but it was a very algebraic proof. I kind of fell back on some very old techniques that you've known for a long time. What I want to do here is I want to give a combinatoric proof, a proof that's not algebraic at all, but instead is based on thinking about counting. Right? So the left-hand side is the number of ways we can choose a subset with r elements from a set with n plus 1 elements. Right? So let me write that. Left-hand side is number of ways to choose an R subset with R elements from a set with n plus 1. Okay, so here's what I want you to do. See what's going on the right-hand side. Let A equal this set with n plus 1 elements. All right, now I'm going to split this set up into two parts. All right, I'm going to split this up into a set A sub n, which has the first n elements, and another set. What are we going to call this? Let's call it A sub 1. And this is a set that just has that last one. Okay. Every subset of the original A, the original set with n plus 1 elements, either has n plus 1 in it or it doesn't. Right? So the number of ways to choose an R subset from a set with n plus 1 elements equals number of subsets with xn plus 1 plus the number of subsets without xn plus 1. Okay, well, that's good, because I remember always have in mind your final goal. I know this is where I want to end up, right? So I know I need to end up with the sum of two things. And more important, I know that these two things have to have this n up here, right? So they have to be based on a set with n elements. So you notice that's what this A sub n is. Okay, so how many subsets, what's the number of subsets without x n plus 1? Right? Well, to make that, I'm going to choose a subset of A sub n, the subset that doesn't have x plus 1. I'm going to choose a subset of that one with r elements. Well, how many ways can I do that? Well, how many elements are there in A sub n? Well, there's n. And I'm going to choose r of them. Okay, now how about this one? The number of I did that backwards. Sorry, the number of subsets with xn plus 1. So I'm still going to choose a subset of A sub n, right? So it's going to have, I'm choosing from a set with n elements. How many do I have to choose? Well, I've already chosen one of them. I've already chosen xn plus 1 to be in this subset. So now I only have r minus 1 left to choose. Okay, looking good, right? Because that's this part. Now let's look at the next part. The number of subsets without xn plus 1. Okay, that's what I accidentally started to say a minute ago. If the subset doesn't have xn plus 1, then I have to choose all r of the elements from A sub n. So I have this set with n elements, and I'm going to choose r of them. And that's the right-hand side. The left-hand side, the number of ways to choose a subset with r elements from a set with n plus 1. This is just n plus 1. Choose r. And there you go. There's Pascal's formula with no algebra at all. Right? We base the argument purely on thinking about counting things and what each of these elements of the formula represents in terms of a count. Okay, so where are we going next? Well, next we're actually going to jump in and start thinking about that binomial theorem. Right? Start thinking about ways we can come up with a really slick formula for writing out big binomial expansions, like say x plus 2 to the 100th. Right? That's going to be our next goal.